Hi, everyone, and welcome to this lecture, Lecture 6 on spherical coordinates and central forces. This lecture is going to finish out our study of Newtonian physics in the traditional sense, and really we just need one big theorem that tells us about central forces and their relationship to spherical coordinates. But in the process of doing that, we're going to work with the spherical coordinate system and do the same kind of derivations we did for the polar coordinate system. So let's hop into OneNote so that we can begin doing that. First of all, let's just define spherical coordinates. So what we're going to need to do here is draw a circle. And then let's turn this into something that looks more 3D, looks like a sphere. Here's our center, and let's continue this equator. Okay, so suppose that we want to describe the point here. So let's actually draw in our axes as well. So here's x, y, and z. And suppose we want to describe a point here, actually. So on this sphere that has some radius, this point, let's say, is in the positive y direction, the positive x direction, and the positive z direction, just for simplicity. Okay, so first, let me drop a line that runs to the x-axis. Or sorry, to the xy plane. All right, good. So in profile, if we have here the xy plane, then this point, which lies on the sphere, which has radius, let's say, out here, this point actually projects down to here. Let's call this point P, just for simplicity. So here is the projection of P into the xy plane. Okay, now let's start labeling the coordinates of this point P. Do note that some math courses will use a different convention for the coordinates than we typically use in physics. So if you learn this in the math department, our conventions may be slightly different. The distance of P from the origin is going to be r. Okay, so let's draw that in. This distance here is r. And I don't know why that turned into an arrow. Let's make it a straight line. There we go. Okay, next we can think about this angle that's in here. So the angle between the z-axis and the ray that goes from the origin to P. This angle we'll call theta. Lastly, we projected down into the xy plane, and we can take a look at this angle that this projected vector makes with the x-axis. We'll call this phi. Projected, sorry. Awesome. All right, so now let's figure out how we would actually find the rectangular coordinates associated with our coordinates r theta phi. Okay, so the x coordinate is going to be this of p, so this is going to be p sub x. The y coordinate would be this is p sub y, and then the z coordinate is up here, so this is p sub z. Now, because we could find the length of this thing right here, it's not that hard to find the px and py numbers, I should say. These ones, so this length here, because there's an angle of theta between the z-axis and r, by some simple trig, you can figure out that this length is r cos theta, which means that px is equal to r cos theta times the cosine of, I'm sorry, this length is r sine theta. That's embarrassing, but it's all right. And that you would see if I drew this here. This length here is the opposite to theta, not the adjacent. All right, so anyway, sorry, that's r sine theta cosine of phi, and py is equal to r sine theta times the sine of phi. Now, pz is the one that encodes the adjacent angle, or sorry, the adjacent side to angle theta. So from here, we see pz is equal to r cos theta. So there we go. Let me actually drop this p notation and say that we have the following map from r theta phi to xyz. X is r sine theta cosine of phi. Y is r sine theta sine of phi. And z is r cos theta. Now we could invert these using, among other things, the Pythagorean identity. And I'll just give you what it is. So r is equal to the square root of x squared plus y squared plus z squared. Maybe not that hard to see this one because r is the distance to the origin, and this is just exactly the distance formula. Theta, well, how would we get theta? The answer is that we could square x and y, take their square root, and that would give us r sine theta. Now, if we divide r sine theta by r cos theta, we get just tan theta. So this gives us that theta is equal to the inverse tangent of square root x squared plus y squared over z. And here, just as in just as in our sort of typical case, we need to be careful. So z could be negative if we're down here, which would make the argument of this arctangent negative, which would output a negative theta. But because theta is defined to be this angle here, it's always going to be positive. In particular, we're going to have theta going from 0 to pi. And let me say it like that. So we need to be careful about which quadrant this maps into. So let me say, always take solution in quadrants 1 or 2. And just use Roman numerals for the quadrants, as that's relatively standard. Give myself a little bit of space, and then I can say that phi is equal to, well, for phi, we don't care about z at all. Instead, that's just equal to tan inverse of x squared, sorry, of y over x. And here we use what's sometimes called the tan 2, which records the quadrant for the angle. So for instance, if y is negative and x is also negative, then we know that this angle should be in quadrant 3 if we know what y and x are independently. But if we divide y by x, we get back a positive number. So the arctan by itself wouldn't tell us this. We need to know what the signs of x and y are independently. Okay, all of that aside, I think many students here have seen spherical coordinates before. And just like for polar coordinates, the new thing for those students will be the spherical unit vectors. So let's go up here and draw in a spherical unit vector. So once again, we're going to focus on this point P. Let me move our label P out of the way, and we'll talk about a basis of vectors at this point, of unit vectors, I should say. Okay, so I'll draw these maybe in red. So again, just like in polar, we're going to have one vector that's collinear with the ray going from the origin to the point P. We'll call that the r hat vector, just as we did in polar. Okay? Next, we need the theta hat vector. I'm realizing I moved my P into a very inconvenient location. The theta hat vector is going to go at 90 degrees here, but in a direction that doesn't change x or y. So it goes, in some sense, you would think, without changing the phi angle. Okay, so here we go. There's our theta vector. Okay, r theta and then phi. Phi is going to be the one that points in this direction, just as it did for polar coordinates. So this is what phi is, but let me draw it in our original system, just so that we can see it more easily. Phi hat. There we go. Okay, good. So it's going to be a little bit involved to define these in terms of the Cartesian coordinates, the Cartesian unit vectors, but we can do it. Let's maybe do that down here, just so we have a little bit of space to work. Okay, let me draw in a circle again. Good. And instead of drawing this sort of in 3D perspective, let me say that I'm drawing this circle so that I am in the plane of the point that I'm interested in. Okay, so this is the xy plane that I've just drawn here. And this is the z direction. There we go. But this is not the x-axis necessarily. Okay, so we take a cross section through the sphere in the plane of the vector that we're interested in. So let's suppose that we're at this point here. This is the point in polar coordinates r theta phi. And here's my ray that goes there. Now, in this system, the r vector is in this plane, r hat vector, I should say, sorry, is in this plane. The theta hat vector is also in this plane. Just point there. And the phi hat vector points into the screen. Good. Okay, but where are the x hat, y hat, and z hat vectors? Well, I can very clearly see that the z hat vector is in this direction. I'll draw these over here, even though we are curious about this point. Maybe I'll call it P again. But where do the x hat vector and y hat vectors point? Well, they don't point straight, out of the board and then over here. So let's, in fact, define vectors that do, and then we'll figure it out in a second. So let me call this the v hat vector, and I'll say that this is the u hat vector. Okay, good. Now let's zoom into the xy plane, and we can look at the relationship of the u hat vector and v hat vector to the x hat and y hat vectors. Okay, so here's a little insert where we'll look at the xy plane. So this is a circle that doesn't have radius r. It has radius r cos theta. Sorry, r sine theta. Man, making that mistake over and over. And here is our point P. or the projection of our point P into the xy plane. All right, so now this is the angle phi. Let's draw in all of our vectors of interest. Here's the x hat vector, here's the y hat vector. Now the u hat vector, maybe it's actually easiest to do the v hat vector, which is in the same plane as our cutout here. So let me point out that this is the plane shown above. This is the plane shown above. So our v hat vector is this vector. And our u hat vector is this vector. Okay, so as a first step, let's get the relationship between the u hat vector and the v hat vector by noting that this angle in here is also phi. Good. Okay, so what do we have? Well, v hat is a unit vector, so the v hat decomposes into the x hat and y hat systems as v hat is equal to cos phi x hat plus sine phi y hat. And the u hat vector decomposes as, well, it's 90 degrees off. So we're going to get minus sine phi x hat plus cos, wrong way. Sine phi x hat minus cos phi y hat. Good. Okay, now back up here. We have u hat and v hat. Let's decompose r hat and theta hat into the u hat and v hat vectors. So, actually, we'll need to do all of them, right? R hat, theta hat, phi hat. The first one that's easy to see is if we look at u hat and phi hat, they're just opposite each other. Okay, not so bad. Now remember that this angle is theta. That means that the angle between the r hat vector and the z hat vector is also theta. Good. So we'll need to decompose r in terms of theta and v hat. And what will we have? We'll have r is equal to, well, the adjacent side is the z hat side, so cos theta z hat. And then in the v hat direction, we'll have sine theta. Great. And what about the theta hat vector, which is like down here? Well, the easy way to see it is that because it's 90 degrees off, we'll have to switch sine theta and cos theta. And then in terms of what gets a minus sign, we just have to look. So it's definitely the z hat direction that gets a minus sign. Good. Now let's take all of this data and copy it, move down here, and we'll stick in the definitions of u hat and v hat. Where's my pasting? Nope, that's wrong. There we go. Okay, so this is then equal to cos theta z hat plus sine theta cos phi x hat plus sine phi y hat. This one is going to be equal to minus sine theta z hat plus cos theta v hat. So this is cos phi x hat plus sine phi y hat. Good. And then this last one, I just need to take the negative of u hat. So sine phi x hat minus cos phi cos phi y hat. Great. Okay, so now we have our complete decomposition of the unit vectors and their definitions. Make sure that you understand these before we go forward. Okay, a couple more things about this. We're going to want to be able to do kinematics, just like we did for polar coordinates. So it's important to note that if we have any object, spherical coordinates are one of the coordinate systems in which we can describe the object's position vector as a vector that lives at the point in question and has the correct length. So if this is an object's position, somewhere on the sphere, but back here, here's my cartoon of the sphere, then we know that there is a vector that has this same length r, but lives at this point. And we can think of this as describing this vector's position. But if we look at the definition of the r hat vector, we notice that this vector is r hat. So the position is given by r hat, and that's always true. This is sometimes represented in the funny equation, funny sounding, I should say. R vector is equal to r hat. Great. Now, if we want to get velocity and acceleration, we're going to need to take derivatives. And the easiest way to take derivatives of these three vectors for a trajectory is going to be to take their derivatives in their Cartesian representation. Okay, we now have the position vector, but we'd like to find the velocity and acceleration vectors in terms of our new spherical unit vectors. So we need to do exactly the same thing that we did to do kinematics in polar coordinates, which is to find the time derivatives of the unit vectors themselves. So I'm going to do something. I'm going to copy these unit vectors to down here so that we can start trying to take their derivatives. Sorry, some stray marks here. Get rid of those. All right, so let's do this relatively quickly. You can repeat this exercise if you'd like. So for r dot, let's go through one line and just figure out exactly what happens when we do all of our chain rule and product rule and such. Okay, so first we'll do the derivative of cosine theta, which is going to be minus theta dot sine theta z hat. Okay, and then plus sine theta. Actually, let me do the product rule on this term first. So plus theta dot cos theta times cos phi x hat plus sine phi y hat. And now we have plus sine theta. We'll do the product rule so that we now hit this whole binomial minus phi dot sine phi x hat plus phi dot cos phi y hat. Okay. And before we move on to theta dot, let's group our terms here. So we'll get minus theta dot times sine theta z hat. Then plus, I'll split it into components. So plus theta dot cos theta cos phi minus sine theta. Maybe you'll put my phi dot up front. Minus phi dot sine theta sine phi. Good. That's in the x hat direction. Now in the y hat direction, we have plus theta dot cos theta times sine phi, and then plus phi dot sine theta cos phi. Okay, let's do the same thing for the theta hat direction and not the theta hat direction, sorry, the theta hat vector and the phi hat vector. So for the theta hat vector, in the first line, we'll just do all of our chain rule and product rules. So we get minus theta dot cos theta in the z hat direction plus theta dot, actually that should be minus theta dot sine theta times cos phi x hat plus sine phi y hat. And then from our second term in the product rule, we get plus cos theta times minus phi dot sine phi x hat plus phi dot cos phi y hat. Great, and then let's do the same grouping of terms that we did last time. All right, and then for the x hat component, we have two minus signs, so we'll just pull a minus out overall. We get theta, oh man, oops. Theta dot sine theta cos phi plus phi dot cos theta sine phi in the x hat direction. And then in the y hat direction, we have a minus for one but a plus for the other, so I won't pull out a minus sign. I'll get minus theta dot sine theta sine phi plus phi dot cos theta cos phi in the y hat direction. Oops, parenthesis in the wrong place. Okay, lastly, for phi hat dot, we have an easier time because this expression reduces more simply. Overall, we're going to have a phi dot from the chain rule from both terms, so I'll just pull that out right away. Then we'll get a minus cos phi x hat, and then a minus sine phi y hat. All right. So now, we're going to have to just do some, or at least it's easiest to just do some guessing to figure out if we can now rewrite these expressions in terms of the polar unit vectors. So let's start out. All right, too many cords hanging around here. Let's start out just trying to see if we see some patterns. So in particular, if I look at all my theta dot terms for r hat dot, so those are all my theta dot terms, do I see those reflected somewhere in the polar unit vectors? The answer is surprisingly yes, right here. So we have a sine theta, or a minus sine theta in the z hat direction. And then in the x hat direction, a cos theta, cos phi there. And then a cos theta sine phi in the y hat direction. So all of this is in fact just theta hat times what? Times theta dot. Good. Now over here, do we see anything similar? Well, we have a minus sine phi plus cos phi. Sorry, I should say minus sine phi x hat plus cos phi y hat. But then times a phi hat sine theta. So this is actually just phi dot sine theta times phi hat. Good. Let's try and remember that. All right, next, in the theta hat dot equation, we'll again look at all the theta dot terms. And let's just try to see if maybe they have something to do with the r hat unit vector. So we get a cos theta z hat, same thing here. Sine theta cos phi x hat, same thing here. And a sine theta sine phi in the y hat. But in this case, we have a minus sign attached to everything. So these terms are given by minus theta dot r hat. Good. Now over here, we want to look for the same thing. And indeed, we find it. In this case, we get phi dot, but times cos theta, times phi hat. Okay, lastly, in the phi hat direction, or not the phi hat direction, sorry, for the phi hat dot equation, we do have to work just a little bit harder because this turns out to not just be some relationship to the phi hat unit vector. Instead, we're going to need to look at the other unit vectors and use some identities. Okay, so in particular, how could we get a cos phi in the x hat direction and a sine phi in the y hat direction? Well, what would happen if we multiplied these by some function of theta and then added them together? Is there some way that we could get what we wanted? So in particular, we want the z hat to cancel out. So let me grab a new color and let's see if we can achieve that. I think to get the z hat vector in the r hat and theta hat directions to cancel out, we should try and multiply r hat by, for instance, sine theta and theta hat by cos theta, and then add them together. So let's look at sine theta r hat plus cos theta z hat. What that would give us is sine theta cos theta z hat. Again, I'm going to first do the sine theta r hat, and then plus sine squared theta of cos phi x hat. Scroll down here so I don't run into my insert. But now I don't have quite enough space. Okay, that's fine. Plus sine phi y hat is what we're missing. Okay, and now I need to do this. So minus sine theta cos theta z hat. Okay, so I have to scroll up and down a little bit. And then now we're going to need to do a plus cos squared theta but notice that what the cos squared theta is multiplied by is exactly the same term as in the r hat unit vector. So we get cos phi x hat plus sine phi y hat. That means that these two cancel, and then we get the Pythagorean identity on the other two things. So we get sine squared theta plus cos squared theta times some other stuff. But this is 1. Great. So what this tells us is that sine theta r hat plus cos theta is, this should not say z hat, sorry, that should say theta hat, plus cos theta theta hat is exactly equal to cos phi x hat plus sine phi y hat. But what we need is the negative of that, so we figured it out. This, maybe I'll stay in green here, this is equal to minus phi dot times sine theta r hat plus cos theta theta hat. Great. Okay, let's put it all together now. So for r hat dot, we got what? Theta dot theta hat, missing a underbar, plus phi dot sine theta phi hat. Okay, next for theta hat dot, we got theta dot theta hat. Is that attached to a minus sign? Yes, it is, and not theta hat, sorry, r hat. And then plus phi dot cos theta phi hat. Great, and then lastly for phi hat dot, we get this thing, minus phi dot sine theta r hat plus cos theta theta hat. Fantastic. Okay, let's return to trying to figure this out. So for position, we had that r is equal to r hat. That's always the case in spherical. For velocity, what are we going to get? but we need to take r dot. Just as in polar coordinates, we can just use the product rule on this product. So that's r dot r hat plus r hat dot. But now we just need to look at what r hat dot is. It's this. Okay, so that's r hat plus r times theta dot theta hat plus r sine theta times phi dot phi hat. Just from right here. Okay, so there's one step in the process. What about for acceleration? For r double dot, well, we just need to use the product rule once again. So r double dot, scalar, r hat, plus r dot, r hat dot. Now there are a bunch more terms. We'll get r dot theta dot times theta hat, plus r theta dot theta hat dot, then plus r dot sine theta phi dot. Actually, let me move the phi dot over. Maybe I should have done that up here too. Okay, then plus, what do we get next? R phi double dot sine theta phi hat, and then lastly r phi dot sine theta phi hat dot. Now this calculation is going to be somewhat involved, so actually let me pull this over to where we have a bit more space so we can work it out. Okay, and the idea here is just going to be to express the unit vectors in terms of the derivatives of the unit vectors and back in terms of unit vectors, and then we'll work everything out in components. Okay, so first let's go ahead and stick in for this term, and this term, the expressions in terms of the polar unit vectors, or not the polar, sorry, the spherical unit vectors. R double dot, r hat plus r dot theta hat plus r dot phi dot sine theta phi hat. Good. Plus r dot theta hat plus r theta dot theta hat. So that'll turn this into a minus. Then this theta dot will become a theta dot squared, then an r hat. Okay, and then this other term we also need to take care of. So plus r theta dot phi dot times cos theta phi hat. Great. Next term we're just copying, r dot phi dot sine theta phi hat. And then lastly, sorry, not quite lastly, because we have to just copy down that term as well, plus r phi double dot sine theta phi hat. And then for the last term, we're just going to copy. Sorry, we're not just copying, we're inserting phi hat dot. So we get r phi dot sine theta, but then because we're taking this thing, we need to stick in another phi dot, so that becomes phi dot squared. And then there are two terms. The first one is minus a sine theta, so that's going to be sine squared theta in the r hat direction. And then the next one will also have a minus sign attached to it. That'll be r phi dot squared sine theta cos theta in the theta hat direction. Great. Okay, now let's use red for all our r hat vectors, r hat direction. Let's use blue for all of our theta hat direction. And we'll use green for all of our phi hat direction. Okay. So when we group everything, we find that in the r hat direction, we have r double dot minus r dot theta dot. Sorry, theta dot squared minus r phi dot squared sine squared theta. Okay, good. Next, in the theta hat direction, we get r dot theta dot, then plus r dot theta dot again. So this just becomes a 2. And then minus r phi dot squared sine theta cos theta. That's all in the theta hat direction. And then lastly, we'll combine all of these ones. Notice that a couple of these terms have nice simplifications. So in particular, this term and this term are the same. So this is going to give us 2r dot phi dot sine theta, plus r theta dot phi dot cos theta, then plus r phi double dot sine theta phi hat. Okay, so this would give us the way that we could solve Newton's second law for spherical coordinates. Great. Okay, so that was a long exposition on spherical coordinates and spherical unit vectors. Basically, I would suggest if you want, then just go ahead and redo those computations yourself so that you've become familiar with them. Otherwise, it's actually quite important for us to move on to the next topic, which is talking about the gradient in spherical coordinates. Okay, so recall that in rectangular coordinates, the gradient of f is the vector field for a function f that goes from Rn to R that takes f to x hat times the x derivative of f plus y hat. In fact, let me just do this for R3, which I guess is what I was doing here. Y hat times the y derivative of f plus z hat times the z derivative of f. All right. Now, that's pretty good, but what we actually want is to re-express this gradient in terms of polar coordinates. So how can we do that? Well, the answer would be we need to figure out the relationship between the r, theta, and phi hat unit vectors and the and the xyz unit vectors. And then we also need to figure this out in terms of derivatives, partial x, partial y, partial z. So this is quite a good exercise to do. Let me show you how you would do it, and then for time, I think I'll leave this as homework for the reader. So what we need to do first is solve for x hat, y hat, z hat in terms of r hat, theta hat, phi hat. Okay, so how would we do that? Well, in some sense, this is just a system of 3 linear equations, right? R hat, theta hat, and phi hat are 3 vectors that are expressed in terms of the 3 vectors, x hat, y hat, and z hat over here. And so by some manipulation, we can figure out what those are. The second is going to be to use the chain rule to figure out the partial derivatives. So I would like to express, for instance, partial x of f in terms of partial r, partial theta, and partial phi. So how would I do that? Well, the multidimensional chain rule tells me how. What I need to do is take partial x of r, partial r of f. that would be the one-dimensional chain rule, but in many dimensions, I now need to take all the other partials. So partial x of theta, then partial theta of f, and then partial x of phi, partial phi of f. And then I need to do that for the y and z directions as well. So how does this work in the x direction? Maybe let's just work this one out. So recall that r is equal to square root x squared plus y squared. That means that dx of r is going to be, well, if I think of this as x squared plus y squared to the 1/2, this is going to be half x squared plus y squared to the minus 1/2 times, by the chain rule, what's inside. So times 2x. Or, in other words, x over square root x squared plus y squared. Good. And then for theta and phi, we would do the same things. Now, we would want to express these coefficients in terms of r, theta, and phi. So for instance, here, I would want to say that this coefficient, rather than being x over x squared plus y squared, I need to rewrite those in terms of r, theta, and phi. And oops, I have made a big mistake just doing this in polar for no reason. Let me repeat this calculation actually in spherical. So r here is square root x squared plus y squared plus z squared. Mostly everything is the same, except in the end, this gives us x over root x squared plus y squared plus z squared. Good. Okay, so now after rewriting this in the correct coordinates, I would get r sine theta cos phi over, well, this square root is exactly r. So this is just sine theta cos phi. So I would stick that in here. Okay. Then I would just plug it all in. Again, we've already done the long calculation of figuring out the kinematics for these spherical unit vectors, so I don't also want to do the long calculation in terms of the gradient, but you can figure it out. And in fact, I'll just come back in a second when I have it written down. All right, so here we go. It turns out that a lot of simplification happens. The important part is that each component still does only depend on that direction for spherical coordinates. So we still do have that the r hat component only depends on the partial with respect to r, and so on for the others. But the theta hat component does depend on this 1 over r factor, and the phi hat component depends on this 1 over r sine theta factor. In fact, because the gradient of f has dimensions of f over length, we needed these factors in order to be dimensionally correct anyway. All right. So now now that we have this expression and we kind of know how we would derive it, let's go and do an actually important result. So I want to return to talking about central forces, which we already defined in a previous lecture. Recall that a central force is a force between two objects. So let me say this is the object A and this is the object B. And what I need is that the force between A and B, so either the force of B on A or the force of A on B, is collinear with the deviation. So what I have is that FAB, for instance, is parallel to, collinear with if you want, RA minus RB. Great. Now, I want to think about a specific case of this, which is also sometimes confusingly called a central force. And that's when I have one object, which is at the origin, so that I'm really thinking of the force just on maybe B. So let me say another usage. So suppose that we have a force that is sourced somehow from the origin and is felt by another object. So here's the object, and here's the origin. So this would say that F in spherical coordinates is always parallel to the r hat vector. And we know that the r hat vector points out of this ray. Good. So we want to be able to say something about central forces and when they are conservative. So question, when are central forces conservative? The reason we care about this, as we learned in the last lecture, is that when we have conservative forces, we're allowed to use concepts of energy in order to figure out something about the dynamics. Okay, so let's assume that we have a central force and try and figure out when it can be conservative. Well, what does it mean to be conservative? What it means to be conservative, as we proved last time, is that it's expressible as the negative of the gradient of some function. We call that function a potential energy for that force. So need F to be equal to, well, we know it's central, which means that I can express it as some scalar F times the r hat vector. And I need it to be equal to the negative of the gradient of u. Okay, so in other words, I need the gradient of u to give me something that only points in the r hat direction. What does that mean? Well, let me express the gradient of u in spherical coordinates using the formula that we just developed. This is going to be minus, from this minus sign here, the r derivative of u in the r hat direction, minus 1 over r times the theta derivative of u, minus 1 over r sine theta times the phi derivative of u. But because I need this to only be in the r direction, I must have that these two derivatives vanish. So true if and only if d theta of u is equal to 0 and d phi of u is equal to 0. But we have a name for a function such that changing either of these angles doesn't change the function. That function is called spherically symmetric. Geometrically, what this means is that if we look at the value of the function at any point on a sphere of fixed radius, so if I draw a sphere of fixed radius, let's say r, then the function's value at any point on the sphere, let's call this point A, and this point B, the function's value at any point on this sphere will be the same. So we'll have UA equals UB for any 2 points on this sphere. Excellent. So in other words, f, this function, this scalar function, needs to be just a function of r. So let me say f of r theta phi is actually just equal to some f of r. Wonderful. So that's the big result of today. I'll say this is a theorem, conservative central force is spherically symmetric. Great. Now we talked last time about how dynamics can be simplified if we happen to be dealing with a system that's parameterized by one variable. Central forces give a really good example of a case where we are not in one actual dimension, but we might have a system which is parameterized by one variable nonetheless. In particular, if we have an object which, initially speaking, only has velocity in the r hat direction, and it's only experiencing a spherically symmetric force, then it doesn't even matter where the object began. We can figure out its dynamics. They'll always be along that one ray. So this is another case where energy considerations actually would be sufficient to give us the dynamics. Okay. The other thing is I said this is true if and only if the d theta u is 0 and d phi u is 0, which means in particular, as long as we're not dealing with any function f that is too gnarly, every f which is spherically symmetric and central is also conservative, which is quite cool. What I would take for u is just the integral from r equals 0 out to the radius in question of f. So let me state that as a second part of my theorem. Every central potential which is spherically symmetric is conservative with u equals the integral from 0, so let me say u of r equals the integral from 0 to r of f of r dr being a possible potential energy. Recall that the potential energy is not unique. So this is a possible potential energy, but not necessarily the only potential energy. And of course, just to be mathematically correct, I should make the variable of integration different from the bound of integration. Okay, wonderful. Now I want to talk about one last thing in this lecture, which is I'm going to keep us talking about the forces between two objects, and we're going to talk a little bit about the energy between the two objects. So in particular, let's imagine we do have a central force between them. So let's call this object A and this object B. This is the case that we were dealing with before, and we know that the two forces between them point along this line somehow. Now, I want to point out one thing that we haven't really talked too much about yet in this class. And that's that in physics, we often expect that certain things are true about the way that physics works in different parts of the universe. So a very common assumption that we make is that it doesn't matter if I run this experiment of trying to figure out the trajectory based on the force between two objects in one point in the universe, or if I go 3,000 light years to the right and conduct the same experiment. We typically expect that the outcomes of these experiments would be exactly the same. In other words, the force between these two objects does not depend, in this case, on whether or not they're shifted left or right. It also doesn't depend on whether or not I rotate this picture. The forces themselves would rotate with my rotation, but the picture would stay the same if I just rotated my head back the other way, for instance. What this means is that I expect my physics to be rotationally and translationally invariant. And there's only one way that that can happen. It's if the force of, for instance, B on A depends only on the distance between A and B. So in other words, on RA minus RB magnitude. Good. But now let's do something sort of clever. We can work in a coordinate system such that A is at the origin. So let me draw in our coordinate system here. So we put A at the origin. Then we know that in this coordinate system, B has a central force in the way that I've just described, this second way of thinking about central forces. So let me say B's force, so maybe I should say force on B, which is FBA, is parallel to R hat in this coordinate system. In other words, it's central. Great. But because it also only depends on the distance between these two objects, it also only depends on R. The other thing is FBA depends only on R if we work in the spherical coordinates in the red coordinate system. So depends only on this distance, R. But that means FBA is conservative. Okay, great. So if we have a central force between two objects A and B, and we have translational and rotational invariance in our physics, then the force between them is also necessarily conservative. Now, in this red coordinate system, I can find some potential energy. Then I can bring it back to any other coordinate system that I want. So here's a rule that comes from this. For any two objects, which interact with each other through forces, we must include one potential energy u of the distance between the objects. So let me say this. Let's call these objects A and B. Okay, now this rule often stumps students who are new to problems like this, who want to include potential energies separately for the two objects. But there's one way that you can kind of think about the fact that there should only be one potential energy that I think is kind of clever. Imagine at first you have a universe where A and B are, roughly speaking, infinitely far away from each other. So they're both at infinity. Now first, we can do, roughly speaking, no work to bring object A in from infinity and to its final position, let's say at the origin. The reason we don't need to do any work is there's nothing else in the universe to exert a force on object A, because object B is so far away, it's at infinity, roughly speaking. So object A can be brought into its position with no force, therefore doing no work. But conservation of energy tells us then that the potential energy at its final position must be zero. Next, we bring object B in from infinity with object A already in place. But if we do that, then object B does feel the effect of object A being at the origin. In particular, it gains a potential energy, U of R, where R is the final distance between A and B. So that's how you know there should be exactly one potential energy for the two objects that come in pairs. The other thing is that if we have more particles, which are present in our system, it's very common that the only energies are still, or the only interactions, I should say, are pairwise. In other words, if we have A, B, and C, then A acts on B, and A acts on C, B acts on A and C acts on A and B. But there's no term that involves some sort of force that depends on all of A, B, and C. So because the interactions are pairwise, we would, in that case, with A, B, and C, end up with three potential energies. One that depends on the distance between A and B, one that depends on the distance between A and C, and one that depends on the distance between B and C. All right. So this mostly, other than working out some problems, concludes our study on regular Newtonian, or maybe I shouldn't say regular, but traditional Newtonian physics. So we can come up with all of these complications, work in new coordinate systems, exploit various symmetries of the problem, define things like momentum and angular momentum. But as we'll find in the next lecture, there's actually still more to do. And it took until the 18th century, really the middle of the 18th century, to start looking at this kind of physics in a brand new way that gets into optimization theory. So I hope that you'll join me next time when we begin talking about calculus of variations and work toward the Lagrangian formulation of classical mechanics. I'll see you then.